Yeah,
Yeah.
thanks. Yeah, great.
Good morning, everybody. So let's start today's seminar. Today's seminar speaker is Dr. Yu-Dai Tsai from Fermilab, and he will talk about his very recent paper, Asteroid G-2 experiment, the new fifth force and ultralight dark sector test. Please start.
Yeah, thank you very much. And thank you very much for the invitation. Let me try to change one that I can see people's face. Yeah, okay, good. So today I will talk about this using the asteroids to study fifth force. And since this is a new paper and we have a lot of different references, if there are some reference that I'm missing or things like that, please let me know. I'll add them to the talk. So in the future or in the slides. So in the future, they are there. Okay. So this paper doesn't really have too much relation with the leptonic G-2 experiment, which you are very familiar with, like the Fermilab muon G-2 experiments. But they are similar in the sense that we're studying the precession. So we're really studying the precession of the asteroids each time, which is very similar to muon G-2. You're studying the muon precession. But of course, the fundamental physics is different. But the reason why we choose this title is also because we realize nowadays the measurement for asteroid is very, let me see if I can fix this, is very precise. The measurement for asteroid is very precise. So how do I change? Okay, sorry. I think did I drop down? Okay, sorry. It's so precise. How can I change the size? Okay, good. So the measurement of asteroid is so precise that you can do some precision study to study long range force and comparable to torsion balance. Okay. So but beyond the asteroid study, I also study a lot of different other things. Like I also study the models, which I will have some of my collaborator. I also told them that they can present the inelastic dark matter. But I also have many other different models that I'm working on. So if you're interested, we can chat afterwards or through email. And I also spend a lot of time building experiments or thinking about new experimental proposal that can probe various different models. And I'm actually also collaborate with or discuss with some of the Korean people about doing midi charge particle study. So there's a lot of different things that you might be interested or I might be interested in your research, so we can chat about them. So because nowadays it's kind of like a renaissance time that people can study different things, and it's very important to collaborate with the experts, but we can also bring our idea to work with those experts. So there's a lot of things that one can study. Okay. So I will talk about asteroids as the main topic, but in the end, I might talk a little bit about some of the other program related to the inelastic dark matter if I have some time. So there's another small topic, but I will focus on the asteroid first. So the main theme of the talk today is to use asteroid astrometry to study new physics. Astrometry means studying the location of the objects, and also maybe also the velocity and the time of these objects. So asteroid is very, very well studied for the following reason. So let me show you why asteroid is so well studied. Actually, maybe I should turn this off so I don't keep looking at this. Okay, so let me share this. Yeah, so this is the video that is very interesting. So you can watch. Let me turn on the voice. Okay, so this is in Russia. You can see there's something coming in to the Earth. It's explosion, yeah. So you might be wondering what this is, and this is, as you expect, is the asteroids. So asteroids, so that's why I'm saying the talk might have some real life consequence, is because these asteroids are really actually could hit the Earth at some point. And from 1994 to 2013, there's all these different events. I'm not even including the one that is after 2013. I think it's because this video was happening in 2013. So the plot that I found related to that is to 2013. So there's a lot of these different events that happen. And interestingly, nothing is hitting Taiwan, but there are some maybe hitting the Korea. So I think so it's very, I think this regime. So it's very serious. And we also know that it's very likely that the dinosaurs are killed by asteroids. So it is very important for us to study the near-Earth asteroid very precisely. And for a lot of reasons, to protect the Earth. If we find out some asteroid is hitting the Earth, then we have to evacuate that area. So it's very important to do that. And that's why asteroids are measured so well that we can do some new physics with it. Okay. And there's another exciting discovery recently I also want to show you very quickly. And there's another video. There is a telescope called Pan-STARRS that is searching these near-Earth objects. And exactly for the Earth's defense reason, because it's worried that some of these might hit the Earth. So that's the second video I want to show you quickly, since I know it's in your morning. So you can see this object is moving very fast comparing to all the other objects. So whenever you see object like this moving so fast, you will wonder what kind of weird stuff is this. And this stuff is indeed very, very weird. It's not a normal stuff. It's very special. It's something called, we call it Oumuamua now. So it is something that is from other stellar system. It's outside of the solar system. It's actually the first non-interstellar object that come to the Earth. So there's a trajectory. So they measure it very well because it's very near the Earth. So you can study its eccentricity. The eccentricity is larger than 1. So it tells us that it goes out of the solar system. So it's the first interstellar object that comes to our Earth to visit us. So there's a lot of people say something like, oh, maybe this is aliens. I don't think I think it's most likely some very weird object. I don't think it's necessarily aliens, but people spend a lot of time studying these. And that's also why they know the shape, because if it's a regular shape, it doesn't explain the trajectory. So it has to have a very weird shape that the sun is heating it up. So it has a very weird trajectory. But anyway, this is another discovery. So there's a defense reason, and there's also an important discovery that was found when they study near-Earth object. Of course, Oumuamua is not a near-Earth object, but it's found when you're doing a near-Earth object observation, because this thing is very faint. So it's only when it's near Earth you can find it. Okay. So here's the outline of the talk. First, I will talk about the planetary precessions from general relativity and solar obliteness, which I will explain both what they mean. Then I will give you a very quick introduction of what asteroids are. And then I will talk about ultralight new physics and fifth sport. So this is the particle physics part. And if you have any question about the asteroid, GR, solar obliteness, please ask me. I'm also learning a lot of these, but it's great to discuss. Then I will talk about the sensitivity reaches and outlook and other interesting projects. Okay, so first let's come with the theoretical breakthrough happened a long time ago. People predicted the precession of Mercury. Okay, so long time ago, someone called Einstein have this idea of general relativity. And then he predicted that, oh, there is a new term that has to be added to the differential equation. So let me explain what this differential equation is quickly. So first, let's only consider planar motion, meaning things are just rotating on one plane. There might be some perturbation that will affect it, but for the simplest case, you can fix to a planary motion. Then you can define inverse radius to be u equals to 1 over r, and u will be depending on phi. Phi is the angle with respect to this planar motion. Okay. And there's also a definition of L. L is the angular momentum per mass, but it also can be expressed this way. And there is this parameter A and E. and these are important. So let me explain what A and E are. A is the semi-major axis, meaning how long is this axis? So perihelion is the nearest point to the sun, but you can average it and found out what is the semi-major axis called A. And eccentricity, as I already mentioned, is telling you how spherical the orbits are. So if it's very spherical, eccentricity is 0. If it's going out of the solar system, then the eccentricity is larger than 1. And you can see all these original, I didn't draw this. You can see the original source of all these plots. So there's a lot of study about these, and it's very interesting to study them. Okay. So and also one more thing that is relevant for our study is inclination. Inclination is just saying that you have a solar plane and there's something orbiting around the solar plane. So this plane is, for example, the equator. So the sun is rotating by spinning by itself. So you have an equator and there will be something that is rotating around it. And then you can get an inclination, which is an angle. Okay. So these are the basics. So once you set up these basics, the general relativity will predict that the Mercury will have a precession. So if you don't have this GR term, there is no precession. But because you introduce the GR, you start to see the precession. And this is actually one of the biggest success. Why? We think GR is correct. So this is an amazing success. And now we all believe in GR. And so GR has different parameter, beta and 2 gamma. So this is the precession derived. So now you can derive from this equation, how does the precession look like? So precession is usually expressed as the change of the angle. So delta phi 0 is the change of the angle in terms of GR. I just defined it this way. And you can see it's depending on A and E, semi-major axis, eccentricity, G Newton, mass of the sun, and the GR parameter, beta and gamma. So each of these parameters has some meaning, but it's not important for our talk today. But they're also called parametrized post-Newtonian parameter, meaning these are beyond Newtonian mechanism. Okay. So anyway, this is the GR prediction. It's very cool. We found out what GR is, but can we find more stuff? Another thing we can find is something called solar obliteness. So the English is very complicated. I didn't know what that means, but it's very easy to understand. It's just how non-spheric things are, how not round things are. So I still need to find out why it's called obliteness, but it's just basically telling you how not spherical things are. And when things are not spherical, it has quadruple moment. So J2 is the solar quadruple moment. From now on, I define as quadruple moment. So because the sun is not spherical, it will also cause a precession. When you rotate in a certain angle, it will also have a precession, things like that. Actually, even if I is 0, there will still be precession. So non-spherical will induce precession, and the leading contribution is from J2 solar quadruple moment. Okay. So why do I introduce this parameter? It's because asteroids, when you study asteroids very precisely, you can actually determine the beta and J2 parameter very precisely. And because of that, we also realize, because you can study beta and J2 so precisely, you may also be able to study new physics. So now we want to include asteroid as some new targets for new physics studies. And if you have any question, please let me know. I'm happy to answer. And well, another fun fact, Professor Moriarty actually studied asteroids. If you don't know who is Professor Moriarty, he's the enemy of Sherlock Holmes. And this is just something very fun to think about. He actually wrote a book about the asteroid, but I digress. So there's many different kinds of asteroids classified by their distance. So today we will focus on the near Earth objects, but I also tell you why the other ones are also very interesting. And strictly speaking, some of these are not really asteroids. These are called minor planets. But most of the minor planets are asteroids or comets. But today we'll focus on asteroids, but even other similar stuff you can study. So I actually say these are all minor planets, and they're classified by their distance from the sun. And I will come back to these. The thing I want you to notice is just how many of them are there. There's so huge amount of asteroids there, which is saying that you can actually study a lot of them to actually do new physics. Because one, you might have some uncertainty, you may not understand it that well, but because you have so many of them, you can study them very well. You can understand a lot of the parameter very well. Okay. Yep. Okay. So this is a table classified by us, but it's already existing in the literature. I just never see this in one place, so we classify them into a table. Okay. So a little bit more words. I will come back to this, but this is just repeating what I said. There are man-built asteroids, Trojan, Jupiter, Trojan. So these are Trojan that is related to Jupiter. And near-Earth objects are not even showing up here because there are not a lot of them. But comparing to there's still a lot of them, but comparing to the man-built, it's not that much. So there's a lot of these here. And people are very interested in studying all of them. And we can actually probe different kind of new physics using different kind of objects. But that's the kind of like future projects. And something called TNO is the trans-Neptunian objects, meaning things further away from Neptune. And these are very, very far away. Not that far as a star, but in terms of solar system, they are almost outside of the usual solar system. So there's a lot of these, and they are subject to less thermal or gravitational effects from the sun or other objects. So these are also very interesting. Okay. So let's get back to the main object. They are called near-Earth objects because they are very near to the Earth and to the sun. So their A is usually smaller than 1, and their eccentricity is listed here. So the eccentricity has to be smaller than 1 because if it's larger than 1, then it's going to the other star. It's not staying in the solar system. So these 9 NEOs has excellent radar observations. So they have very good data. So these very nice UCLA group use this to study beta and g-2, as I mentioned, to study the GR parameter and solar ablateness. Okay, so a few words about radar data. The radar data is very precise. So when I talked about this project to a lot of my friends, they are very skeptical. They ask me, why can you have such a high precision? The reason is because radar. One reason is because radar. Because radar can really measure things very well. Because you can, when I say radar, it's not just radio signal. People actually send the microwave to the asteroids and come back, so you can measure its time. And also you can study the Doppler effect. So it's very precise. And this KW4 is especially studied very precisely because KW4 can hit the Earth. So this is the dangerous one. That's why I mark it. And you can see the uncertainty of the distance is very close. So that's why it has to be studied to such a high uncertainty. So this is uncertainty to the distance to the Earth. So you need to understand the uncertainty very well because otherwise maybe it's hitting the Earth. So you need to know how far away it is. So this is one of the most dangerous asteroids. Oh, there's a lot of dangerous asteroids, but this is one of them that we study. So it's very interesting. Yep, let me keep going. Now we first study by the UCLA group, but we also use their result to do new physics. Okay, so radar data, as I say, consists of round trip lifetime, which I will explain what it is, and Doppler shift. So Doppler shift, we all know what it is, but round trip lifetime is also very easy to understand. I will show you in the other slides. And the precision is 10 to the minus 8 fractional uncertainty. So fractional uncertainty means that if you measure something like 1 kilometer, then the uncertainty is 10 to the minus 8 times 1 kilometer. So it's very, very precise. When you talk about cosmological measurement, a lot of times the precision is order 1. But radar data is 10 to the minus 8. That means you have a lot of precision. And you can use range and Doppler. The first is usually the range, the second is the Doppler. So you have all of this data for these 9 asteroids. So these are the total amount of data they use for these 9 asteroids. And yeah, so round trip light time is just when you send the microwave to the asteroid and it comes back. This is the time it takes. They can count it. And for example, to the sun, if we send a signal, microwave from Earth to the sun and come back, it takes 17 minutes. And the Doppler shift, we all learned this in high school. It's when you're moving near to the asteroid, you can see the microwave will get more, the wavelengths will change. So these can measure the velocity. So you have the location and the velocity. So you have a lot of information that you can control to understand the asteroid trajectory. Okay. So the analysis, so they go through the very complicated analysis. I will not get into a detail, but they basically have to model the trajectory of each asteroid. And that's actually being taken care of because, as I said, we need to study this near-Earth object very precisely. We need to know if it will hit the Earth. So there's already a program to do that called Monty. So they model the trajectory and they fit the 56 parameters. So 9 times to 6 of these, 54 of these are called orbital elements, meaning what the things that quantify the orbits. And 2 of them are beta and J2. So they fit all this data. I consider some covariant matrix analysis is very standard. And they also do a Monte Carlo, but I will not get into detail. And this is their final results. They can constrain the beta parameter to a very high uncertainty and J2 also to a very high uncertainty. This is not the world best limit, but it's quite close. So that's why it's very interesting to study asteroids. And for the 2022 projection, these both are like kind of projection, but they also have an optimal projection that is a smaller number. If they assume like what they say is the first line is more conservative estimation, and the second one is more more realistic one. And we call it optimal for our result. So we use both results for our new physics study. Okay, so these are asteroids and all these different GR stuff. Let's look at the ultralight dark sector. So if you have any question, please feel free to, I think you can raise hands or something like that from the function, and I'm happy to answer. But otherwise, I'll talk about the ultralight dark sector. So this is now the thing that we're more familiar with as particle physicists. So first of all, you can introduce your Yukawa potential 2 different ways. It's the same thing, but different parameterization. So you can say, what is the new physics term in terms of comparing to the G Newton? So you can have an alpha tilde, which is just a strength of the long range force. And then you have a length of the drop off distance that the long range force will start to drop off in a certain mass, in a certain length range. And this is directly correspond to some kind of long range Fives force. Let's say you have a G coupling, you have the charge, total charge of the sun, total charge of the asteroids, and also the mass of the mediator. So this is kind of Yukawa. It's like a pion, but very light pion. So we all understand what that means. And once you introduce these terms, it will come into, so there's a complicated derivation. We derived it, and previously Potter and other people also did a very careful derivation. So you can read up this paper. So it goes through a complicated derivation, and you come to here. And this is the new physics contribution. So, so you have gauge boson or dark photon or scalar, they can all create this kind of long-range force contribution. G is the new physics coupling, M is the mediator mass. Okay, So we pick two specific model. One is gauged U1b, and another is baryon-coupled ultralight scalar. So for gauged U1b, we just call it GA prime for whatever reason. It's the long range force. It's the gauge. It's a dark photon. It's the gauge dark photon. We call the coupling GA prime. So the dark photon will be A prime from now on, and we just charge all baryon equally because it's U1b. And for baryon-coupled ultralight scalar, it's very similar. You have a scalar coupled to these proton and neutron the same way, and phi is very light. That's it. Very simple model. But the U1b is, of course, anomalous. Everybody knows it's chiral anomaly. So you need some heavy particle to cancel it, and there are some accelerator constraints. I will not get into detail. And then you may be able to you may be able to build some model to alleviate the constraint by, for example, Green-Schwarz. Okay, sorry, this is misspelled. Green-Schwarz mechanism, or Kaplan has a composite model. Then maybe you can alleviate the constraint. But anyway, this is the phenomenological model that we go with. And our study can also be applied to U1b minus L, or LE minus L mu, LE minus L tau, all these different models. But these are a little bit more complicated because you have to charge. So B minus L, you only charge a neutron. So you have to know how many neutrons are there in the sun and in the asteroid. So it's more complicated. So that's why we do just U1b. LE minus L mu and LE minus L tau is easier because electron, you can count how many electrons are there. But there's also the neutrino bound, which is very strong. So we use U1b as an example for now. But our analysis can be directly recasted for B minus L or LE minus L mu or LE minus L tau. Okay. So this is the new physics contribution to the precession in the low mass limit. So when your mass is very small, when you have n much smaller than 1 over a, 1 over a is the inverse of the semi-major axis, you get this expression. This is the precession caused by new physics in a closed form. So we don't really use this. We just use this for an analytical understanding and check our results. But we actually solve the actual differential equation. We actually solve this equation 3, but there is an analytical result. So this analytical result is extremely interesting because you can compare this to GR effect or the solar effect. Sorry, this is blocked by the plot. But the key thing here is, even though it's very simple, it's also very meaningful because new physics effect is positively depending on A, meaning that if you study things farther away from the sun, it's advantageous. So you want to study things further away from the sun. But for GR, this is inverse to A. So all you need to do is to study like Mercury or things very near to the sun. Then it's enough. So that is also why people didn't really study things further away from the sun. Because if you only care about GR, you don't really need to care about all the other things. But because we care about new physics, we want to study things beyond the near Earth object. We want to study the man-built asteroids. We want to study Hildas, Trojan, Jupiter Trojan, or TNO. That's why we want to study things further away. So that's why we should explore objects further away from the sun, and not just Mercury or other planets, because those are limited by their A. And also, this term is not really depending on the asteroid's mass. So even the light stuff is fine. You can also study things that are light. It doesn't matter to your results too much. So this is a cool equation to look at and know what we can do for the future. Okay. So now we are going to the final, almost the final step. So now, okay, so this is the phenomenological thing that we do. So we solve for new physics, and we say that the new physics contribution has to be smaller, roughly smaller, or the same order as the uncertainty from beta and J2, and also, of course, the correlated term. So we just directly use this very simple requirement. We list it in our paper to set the sensitivity reach. Why do we do this? It's because we're saying we should be able to measure the parameter G, the new physics coupling G, to the same order as beta and J2. And these two terms are actually about the same size. So this first term and second term are almost the same. So it's saying that all three parameters should be able to reach the similar uncertainty for this measurement. And that's what we're claiming. That's why we're doing this analysis to see what's the actual, not the actual, what's the rough sensitivity. And because there's 9 asteroids, we have 9 results, but they're all very close. So let me just show you the results. So we did this, and these are all the results, and they are very close to each other because they are comparable, because as you can see, their parameter is very similar. So we have 9 results. So again, we solve for the equation, we solve for the new physics and require it to be smaller than these results. And the uncertainty budget for the precession for these results. And you can see that the best reach are from the TU3 asteroids, MN asteroids, and BD19 asteroids. So we kind of combine all of them, the best one, into this one curve. And also we do a 1 sigma and 2 sigma curve. And also because they have an optimistic results, we also did an optimistic sensitivity reach. So this is roughly the sensitivity reach. And we also label the range of interest for, so this is for NEO, this is the best, sorry, this keeps moving, sorry. So the best sensitivity usually is corresponding to their semi-major axis. So roughly speaking, the best sensitivity is corresponding to their A. So NEO is the best for this regime. Main-built is best for this regime. JT, Jupiter Trojan, and Hildas is best for this regime. TNO and ETNO are for further regimes. So eventually you can probe this whole regime, I think. But we still need to do those analysis. Those have larger uncertainty. So we need to really, or worse measurements. So we really need to go and understand all the difficulties there. So this is just for the future. But these are the current results. So let's compare these to the bound. So you can see there is torsion balance bound. And we actually can do better than torsion balance. This is quite surprising to me because I thought that we cannot do better than torsion balance. But based on this kind of naive estimation, we could do better. So this tells us that we should probably do a very detailed analysis. We should add the new physics term to the Monty simulation and do almost exact same thing as this UCLA group, but with more asteroids. And maybe we'll get a better results. And I will comment why I think we'll get a better results. And so there's a torsion balance. Surprisingly, we can do better. And there's also super radiance. Super radiance is done by a lot of people, but super radiance only apply to the A prime. It doesn't apply to phi because phi, A prime and phi vector and scalar are very different for super radiance for this range. So the super radiance bound currently does not apply to scalar. So this bound does not apply to scalar right now. Also, if you want to study the scalar super radiance, you need to understand supermassive black hole very well. So that's not yet being studied very well. And there's also the lunar laser ranging. So lunar laser ranging is very similar to asteroid study because lunar laser rangings, you put a mirror on the moon and you shoot a laser to the moon and it comes back. So it's very similar to radar astronomy. So they can also do very well, but they do well in a higher mass. So the best interesting range doesn't really overlap. It's because the sun and moon, sorry, the moon and Earth distance is much shorter. So it's a different parameter. And of course, there's also planet. Planet can do pretty well, but since we have a lot more asteroids, we can probably do better in the future. So, but before I go to the more asteroid thing, I also want to say that even though there's many different bounds here, they are not the same bound. not all the bounds are created with the same assumption. All of these other bounds, torsion balance, superradiance, or actually just torsion balance and superradiance, they're assuming different physics. Torsion balance is a short, long-range study. It's only on the Earth. So they don't really probe the very long-range physics. They only probe the model, but they don't really probe the long-range force. Superradiance is the same. They probe the radiation, the kind of like radiating out these dark photon, but they don't really probe the long-range force. So there are some very weird model that only has long-range force in the long range, but doesn't have long-range force in the short range. So maybe you can alleviate the torsion balance or superradiance bound. So alleviate in the different ways. So you can alleviate the torsion balance by saying that maybe there's some crazy model that you can have long-range force in the large range, but no fixed force in the short range. For the superradiance, you can say maybe there are complicated dark sector that the radiation will be impeded, like the dark photon doesn't come out for some reason because there's dark matter around the black hole. So there are maybe ways to get around these bounds, but asteroids and planets are actually probing the long-range force in this range. So these are the actual long-range probe. So even though the bounds are comparable, these are still a new bound. This is what I want to say for the physics. Of course, for the model, it's the same parameter. Okay. Yep. So this is what I want to say. Okay. So one more thing I want to say is that there is 2,000 near-Earth objects. They are the same level of precision as these 9 asteroids. So we really should go study all these 2,000 near-Earth objects. And every day there's new near-Earth objects being found and being studied very well. So we can really potentially improve this by 1 order of magnitude or 2 order of magnitude. Maybe 1 order of magnitude is possible. So maybe at least we can maybe reach this optimistic range for 2 sigma, or maybe even better. But we really need to run the whole program. So that's something we're developing right now. So let me see how much time. Okay. So also I want to come back to this. So as I introduced to you, there's near-Earth object, there's man-built, Hildas, Jupiter Trojan, trans-Neptunian object, extreme trans-Neptunian object. The number is different, but they are also classified by their distance to the sun. So combined with this equation, you know that you want to study further and further away to start to fill out this range. So the curve for a man-built will look like this probably, and then Trojan will look like this, TNO and ETNO will look like this. So they will maybe be able to just go up like this. But we're not sure yet. We need to really do the study. And there's also a very interesting study, like maybe these are related, maybe long-range force is affecting the relative astrometry. So there's a lot of things that one can study. I'm thinking about a lot of these, or oscillation, whatever. There's a lot of interesting related models that one can explore. And if you have some idea, I'm very interested in chatting with you about the new model that you think about. And this is a TNO. So I want to emphasize TNO is better for some sense, because for the near-Earth objects or all these different objects, they are affected by each other and also by the heavy planets. But when you go to TNO, they are very far away. So they are subject to less gravitational perturbation or solar thermal effect. So the sun will not heat up this TNO to affect its trajectory. So since they are farther away, it's actually better in some sense for new physics study, because there's no other systematic errors. Okay, so that's the kind of the physics discussion. How about observations? So observation, as I say, for the radar, you have the Goldstone Observatory. This is one of the best. It's sending like radar and coming back, so you can do a lot of this study. And this figure is by Laura Hartley, and it's like a very cool picture for the radar observation. For optical, there will be this Vera Rubin Observatory. So Vera Rubin is one of the first leading person to find or identify dark matter, the existence of dark matter. So it's very exciting, and we name it's very deserve that we name this observatory with her name. and Vera Rubin is amazing in that you will find a lot more solar system objects. So you will find a lot more solar system objects that you can use to study the thing that I talked about today. Gaia is also very useful indirectly because Gaia can study the sky, not the sky, sorry, the stars very well. So Gaia can study all the stars very well. So the star become a reference for the asteroids because asteroids themselves does not have light. So you have to use the sunlight to reflect. And also there's no coordinates. So if you look at the sky, you want to identify the location. If you just use optical, it's hard to identify a location. But if you have other stars, you start to have the reference frame. So Gaia is actually very useful in providing that. And my friend, Dr. Marco Micheli, he's one of the ESA person. He gave a talk on Monday about the new advancement of the Gaia. And he said that Gaia is a new game changer for this kind of near-Earth study because it provides this stellar reference frame. Okay, so it really helps the localization. And finally, there's mission. So we actually can send people to the asteroids. Actually, Obama wanted to send people to the asteroids. I don't know why, but Obama tried to do. I think there's a plan, and I don't know if it happens. I think it didn't happen. But Lucy is not really sending people to the asteroids, but it's going to visit the asteroid. So want to study the asteroids. So you have a lot more information about asteroids by having this mission. And there's many other space missions. I don't know if Korea is involved, but Japan is involved. Japan has this JAXA that they have something called BAPI Colombo. Yeah, BAPI Colombo that is also going to study the asteroids. So there's a lot of study. And these are near-Earth objects or further away from the Earth, but you can go there like in 1 year or 2 years. So it's not that far. Well, 1 year, 2 years probably, yeah, 1 year or 2 years, or even shorter time. So it's not that far. Nowadays, we can really go there. If you want to go there, it's possible. Well, I think if you are Japanese or US people or Russian, it's easier. But maybe Korea also have a space mission. I'm not sure. I think it's very hard for Taiwanese people to go because we don't have oh, if you're Chinese, maybe you can go. But yeah. Anyway, so let me give a big picture. So planetary astrometry is a strong new tool to study new physics, has many more models and related new techniques. Planetary astrometry has defense purposes because you don't want them to hit the Earth. And if it's hitting the Earth, you need to evacuate. You need to tell people to leave the place. And it has a significant discovery, made this significant discovery about Oumuamua. Oh, by the way, maybe I forgot to say, the Russian asteroids attack actually injured 1,500 people. So 1,500 people have to go to a hospital because of that. So it's serious. I don't think people died, but many people have like small injury. And our result is exciting by itself. We also have significant potential given the future measurements, including radar, optical, space missions, will bring tremendous progress. Okay. Okay. So there are many other interesting projects, but if there are some quick questions, you can feel free to ask me. But oh, actually, it's almost the time. So yeah, if you have any question, you can ask me. But if not, I can also say a few words about the other experimental program related to inelastic dark matter.
Excuse me. So may I have a quick question?
Yeah, please.
So what is the motivation to study this kind of a very light particle with this tiny coupling?
Yep, that's a great question. So so first of all, yeah, I should add that in the intro. Sorry, I forgot to add that in the intro. So in this range, you can see this is 10 to the minus 20, 10 to the minus 21, 10 to the minus 19. this range of the particle, if they are dark matter, they are the fuzzy dark matter.
Right.
So they can affect the galaxy structure. So even though we don't assume them to be dark matter, they can be dark matter. And there will be some other effect that we can also study on the asteroid. So I'm actually thinking about that right now. I'm not sure if it will work out, but it might work. So they can also be dark matter. But even if they're, I mean, this is still a bound on all these things. So this is still even though we don't assume it's dark matter, this will still provide a bound on the dark matter. So dark matter is one motivation. Another motivation is, sorry, I can tell you, sorry, do you have a question?
No, I see. Yeah, thank you.
But that's only one. There's also string theory, also predict this kind of very light particle. So dark matter is one. String theory also predict many of these dark light particle. And there is another one that is related to the dark energy. So this model that I told you is very odd, that only has long range fifth force, but doesn't have short range fifth force, is one of the model to explain the things in the cosmology. This is called the chameleon model. So this paper is called Chameleon Cosmology. So they introduced this kind of long range force to explain something in cosmology. You should read the paper, it's pretty interesting. The model is a little bit weird, but the physical effect is quite interesting. So this is chameleon cosmology. So this is something. So there are roughly three main motivations, like dark matter, string theory, or cosmology. But there might be other motivations I haven't thought about, but these are the three motivations. Thanks for the question.
Yeah, that's very interesting. Thank you.
Can I ask one question?
Yeah, please.
So in the measurement of this angle, theta phi, so you could also have some interaction between NEO, I mean the near Earth object. Does it have any effect on this measurement?
So you're saying between the two near Earth objects, right?
Yeah, exactly.
Not really. So near Earth objects are way too light. So their own gravitational effect does not affect each other.
So the fact that the Earth is heavy is important in this case. Okay.
Earth has some importance, but not just Earth. Actually, everything is important. So in the Monty simulation, you have to take into account the perturbation from Mars, Venus, Earth, or Mercury. All of these important bigger objects you have to take into account there.
So they are taken into account, but the asteroids are light, so you can just ignore those the interactions among them. Okay, thanks.
Yeah. But you even have to take into account, for example, Jupiter, even though it's further away because it's massive. But the interesting thing I realized is these are still perturbation, because even though there's many planets, the sun is still way heavier. So there is an order of magnitude difference. So yes, the perturbation is important, but you can still treat it as almost a two-body. Because if you have to do three-body, then things will become chaotic. But still, it's roughly a two-body plus perturbation from the planet. But that's a great question. Yeah.
Okay, thank you.
Yeah, thanks. Yeah, feel free to ask.
I have a further question about that.
Yeah.
So you said the angle phi is linearly proportional to the A.
Yep.
For the new physics, and A inverse for the gravity.
Yeah.
This is mainly for the solar, right?
Wait, actually, let me get there. Actually, it's not just linear. Actually, it's
square. And the gravity part is only for the solar, for the sun, right?
Yeah, so this is a weird thing. Okay, that's a great question. I actually don't understand why, but you can see. So you see, the GR effect is proportional to the mass of the sun. But the new physics does not care about, at least in the limit, in the low mass limit, does not care about the mass of the sun. So it drops out. So this is, I went through the derivation again, and there's no dependence on mass of the sun. So it's weird. But it does depend on the mass of the sun if you solve the differential equation. It's just in the limit, the mass of the sun doesn't show up. So it's corresponding to this regime. Sorry, it's corresponding to this line. And this is very, very accurately described by the analytical result. But I think you have a slightly different question, right? So sorry, what was you're saying with respect to the sun?
So you studied about the near Earth object, but you also said the other more far away object is also could be very important.
Yes.
But in such case, so the A is much larger than 1, then I think the sun is also important for gravity, but also Jupiter or Saturn, kind of a planet, their gravitational effect will be also very important in that case.
That's absolutely right. Yeah, you're totally right. So that's related. That's related to the previous question. So when you run this in the beginning, I say that for the analysis you have to run this Monty thing, right? So where is the Monty? I described it somewhere. Asteroids. Sorry for the somewhere. Yeah, wait. Sorry, Monty analysis. Yeah, here. So there is this program called Monty, or maybe it's pronounced differently. But these take into account the gravitational effect of all the different objects. So if you want to study further away objects near the Jupiter, yes, the Jupiter effect will be very strong. So you really need to take that into account. And maybe not just the gravity effect, maybe also the new physics effect. Because even though the new physics strength is very small, so the new physics is actually very small, very tiny. As you can see, the alpha is very small. So alpha by itself is very small, 10 to the minus 10, and 10 to the minus 6 to 10 to the minus 10. So the magnitude is very small. But because it's a kind of a new contribution, so it might have some unexpected effect on the trajectory of all these asteroids. So that's actually something I'm thinking about now, because it does have it could have some interesting effect. I'm not sure yet, but it could have some interesting effect. And yeah, all of them should. So in principle, if you have a quantum computer, then you want to take into account all the different perturbation from any different objects, also including the new physics. But in reality, you need to check what's the leading contribution. So there are some order of magnitude estimation, like you have the comparison of the mass of the sun to the planets to the near Earth objects. So there is an order of magnitude difference. So sun is the most important, then Jupiter, then other planet, then the near Earth object. So there is an order that you can expand around. So they should be taken into account. So I'm learning from Marco and David. These are the asteroid people. They are familiar with the asteroid. I try to work with the UCLA people, but I haven't been able to chat with them directly yet. I chatted with one of the author. I chatted with Greenberg. Greenberg is I chatted with the third author, but he's not working on this directly nowadays. So that's why I need to chat with Verma and Margaret to really run the Monty and add new physics contribution. And there may be other new physics contribution one can add to test the new physics model. So yeah.
Thank you.
Thanks. Oh, so I think we're at out of time. So I don't think we need to go to the programs. Maybe I just show one photo. So I know a lot of people are studying the inelastic dark matter, which may be related to muon G-2, and I'm very interested to chat more about this. So there are some new constraints you can set by accelerator experiments, and I also propose one experiment called Long Quest at Fermilab that might be able to search for this long-lived particle that you produce this inelastic dark matter in the collision, and you can study it downstream behind this iron block. So you put a new detector here. So this is there's an original idea, it's not from me. There's something called dark quest that they want to replace this wall and put a detector here. But my kind of new idea is to say we don't have to do it here. We can do it behind this iron block, so the signature is cleaner. So you can search for inelastic dark. Sorry, you can search for dark photon. Sorry, you can search for inelastic dark matter decay into E plus E minus and chi1. So chi2 decays to E plus E minus and chi1. And I know some of you are studying similar models, so this is one of the experiments that can probe that. But anyway, so let me conclude. So you can so it's very exciting time. There's a lot of different tools. So I'm very interested in chatting with any of you about the new thing that we can study, whether it's using asteroids, other objects, or accelerator to probe our different kind of model, whether it's an elastic dark matter model or the thermal dark matter model that you propose. Thank you very much.
Thank you very much. Any further questions from audience?
So in your experiment, the mass of the new particle around 10 to negative 17 was the most sensitive one because of maybe the combination of all these interactions.
Which experiment or which observation?
The measure of this by measuring this delta phi, you had some sensitivity plot of the coupling versus the mass, and the 10 to negative 17 and 18 was the most sensitive one. What else can you? I mean, this is a very naive question, but if we want probe like a much smaller scale of the masses, then what else experiment can you do?
Yeah, that's a great question. So, so that's a excellent question. So, why is the best sensitivity here? It's because two competing effects. One is that because when your mass is too heavy, there's an exponential suppression, right? So the Yukawa term has an exponential of the mass. So that's why it drops, right? And on the left-hand side, you also drop because when your mass goes to 0, your potential become 1 over r, right? And if you have 1 over r, you don't have precession because 1 over r is Newtonian. So if your mass is 0, even though so maybe your alpha is 100, like very large, but if your mass is 0, you still don't have any precession. So there is a competition between the two, and the best range is about the same as inverse semi-major axis.
Okay.
So that's why this is important. So this A is the semi-major axis. So when near Earth object, when you consider near Earth object, that A is A times 1 minus E is smaller than 1.3, then it's corresponding to this regime. And that's why this regime is best for NEO. But if you want to study different mass, then you want to study Manbel, Jupiter Trojan, Hildas, TNO, and ETNO. And if you want to study things here, it's also possible, but you need to study maybe other kind of, let's say, flying object that I have not thought about too much, but it's possible. Like since you see you can study the moon to probe this regime. So there's something in between. So this is the moon-Earth difference. So the moon one also look like this. So there is a distance that is best for the moon-Earth difference, this distance.
Okay.
So maybe there's some object in between that you can study to probe this region. So there's a lot of other objects that, so as I say, the planetary astrometry is kind of a new field. It's interesting that nobody actually explored it yet, but there's a lot of objects that one can study.
So in terms of the observatory, the uncertainties, so as you go away from the NEO to the more far object, does precision remain the same or they drop significantly?
It drops significantly.
Okay.
Because because you can no longer use radar. The reason why you can use radar is because these things are very near Earth. So when it comes to near the Earth, you send the microwave to them and it comes back. So when it's very near the Earth, you can do that. But when it's further away, you don't have radar. But my friends in asteroid study, they told me it's not that bad because you have spacecraft. So sometimes we'll send spacecraft to actually those places, like the main build is possible. So with the help of spacecraft, maybe you can keep some uncertainty, and also the space telescope like Hubble or other stuff. So in the future, maybe it's not that bad. So right now we really rely on radar, but there's a lot of other optical or spacecraft. Those might be very well in helping those measurements. Like spacecraft can do almost as good as radar. That's what they told me. I don't know if it's true, but it's great to chat with all these asteroid people because they really know the measurement. So yeah.
Yeah, but spacecraft sounds very good idea.
Yeah.
Okay, thank you.
Yeah.
Hello. Hi. Thank you very much for a nice talk. And in this plot, the most sensitive value for M pi is corresponding to around 0.8 AU in terms of the computer wavelength.
Yeah.
It's roughly the distance with about 1 AU, right?
Yeah.
Is there some simple reason for that?
Yeah. This is basically corresponding to this one. So because the A is around this regime. So basically the best precision is determined by this TU3. The TU3 is the best measured asteroids.
Okay. I see.
That's why it's around that that mass. Yeah.
And another question is, you have some materials in the backup slides.
Yeah.
Do you have something you like to emphasize, or I mean?
Yeah. So I know a lot of you, especially Pyong-Won, is thinking about elastic dark matter. So sorry today I didn't have too much time to talk about these or to learn from you guys. But yeah, I think in elastic dark matter, there's a lot of interest there. So once you build this accelerator probe, you can study the decay particle. And if your elastic dark matter is decaying to Chi1, E plus E minus, you can search for them. And one thing I want to emphasize maybe is related to the actual G-2 experiment. So I think maybe you also studied this. I need to read your paper more carefully. But there is a band for muon G-2 because the A prime can be used to explain the G-2. But this regime was actually excluded. But recently there's a paper by my friend Mola Bang to say that you can avoid this bound by having semi-visible decay.
Yeah.
So yeah. So in a lot of these electron collider, you can use semi-visible decay to avoid the bound. And for accelerator search in the visible search, you can also avoid it because things actually decay away before they reach the detector. So there was this band, but maybe right now you can also close it by other experiments. So I just want to say that there's a lot of study that can also be related to muon G-2. And also you can also study mini-charged particle. There's a lot of different design that I propose that we can study mini-charged particle, but there's also maybe other stuff that we can do, like using cosmic ray production or using the LHC forward physics regime. So I just want to say that there's a lot of different study we can do for mini-charged particle, and maybe you also have some mini-charge model that we can also apply to this experiment. That would be interesting. And yeah, I'm very happy. I'm very interested in learning the model that you consider. Yeah, thanks. That's all I want to say. Yeah.
Okay, thank you.
Yeah, thanks a lot.
I have a question about the long quest.
Yeah, go ahead. It's a proposal, but yeah, go ahead.
It's a proposal, not a fixed yet.
Yeah. So I can say a few words about this. So this experiment is currently called spin quest. The reason why it's called spin quest, it's because it's studying the quark spin. So it wants to have two protons, so you have a proton hitting the target, and there will be Trojan process, and they want to use that to study quark spin. I don't know why, but there are some nuclear reasons to study quark spin. So now the idea is to say, maybe in the future we can remove this thing or put a detector in front of this wall to search for decay particle. That is called long quest. Well, sorry, that's called dark quest. But I think you can actually you don't have to do it. The best way is actually to right now put a detector behind the iron block to search for decay particle. And that's what I call long quest. So you can actually do it right now. But I haven't got funded yet, so I don't think I can do it yet. But there are a discussion of how to get funding for dark quest and long quest, that is happening at Fermilab. But certainly it's not yet realized. And I know there are some facility in Korea or in Japan that also have similar structure. Like in Japan, there's this J Park that you can also do some this kind of study. And I know there's a Korean experimentalist that is in charge something to search for mini charge particle. I forgot his exact name, but he actually got some funding to study mini charge particle there. So there's a lot of interesting thing one can think of, like the low cost detector. So if you're interested, we can chat more. Yeah. But this is just a proposal for now.
So how far from this you locate the new detector?
Yep. So
50 meter.
Yeah. So roughly speaking, the total distance from the target to the detector is 30 to 40 meter, because this is like 25 meter. There's a 10 meter iron block. So roughly total, there's like 40 meter away. So it's not very far. So this is way nearer than, let's say, other kind of experiments. So it's actually pretty nearby. And dark quest is even more near. It's like 25 meter. But I'm worried that the background will be very large. So there's a lot of simulation effort into doing the background. But doing things here is very clean because there's 10 meter iron block to absorb the background. So things are very clean here. So this is something I think can really work. Yeah.
So I have some confusion. So in this case, in this cartoon, actually the gamma prime decays in the first block and then detected within 25 or whatever. But now in your proposal, actually the gamma prime is a long-lived, and so it survives through this iron block and then decays in the E curve in the last block. Okay, so
Yeah.
then what's your target range of the coupling and mass in this case, given this the dimension?
That's a great question. I actually don't have yet I'm still working on the sensitivity for this one. So previously we did one for, I call it long quest one. I just say that we add some particle ID here to study the long range particle here. But this one is a little bit far away, so I don't have a sensitivity plot yet. But it's very similar. It's not that far away, so it's actually very similar to this long quest one, but a little bit lower. So it will be cleaner. So the background will be better. So you can reach smaller epsilon, but you also will lose some sensitivity because some particle already decay away. So you will be the upper curve will drop down a little bit.
Okay.
Yeah. But that's a great question. Yeah. So the parameter is a little bit lower down. Yeah.
Okay.
Yeah.
Thank you.
Thank you.
Okay, is there any further questions?
Sorry, Omar. So the reason why it has upper and lower bound is the upper bound is because if it's epsilon is too big, you cannot penetrate the iron block. Is that the reason?
No, it's not. No, there's no problem penetrating if it's long-lived particle. The only issue is that it will decay away before reaching the detector.
Oh, exactly. Okay. So if epsilon is bigger, okay.
Yeah.
Thanks.
But it's not that different because it's
Mhm.
not that far. Yeah.
Okay.
So yeah.
Yeah. Fine. Okay. Thanks.
Thanks.
Okay. No more questions from audience? Okay, very good. Then let's thank you to Yu-Dai. Very nice talk and discussion.
Yeah.
Thanks for the nice seminar.
Thank you. Thank you very much.
Thank you.
Thanks a lot. Thank you for the
Thank you very
invitation.
much.
Thank you.
Yu-Dai, could you please send your slide?
Okay. Yeah. I will clean up a little bit. Yeah. I'll remove some of the more sensitive one and yeah, some of the I will definitely send you. Yeah.
Bye bye.
Thank you. Bye.
you.
See you. See you in the future. See you.
Bye.
Bye bye. See you. See you maybe in Taiwan. Yeah. Stop sharing.